Okay, let's take a look of this binomial theorem. Okay, binomial theorem is something similar. You have a something like 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Is that okay? So 1, 3, 3, 1, you can write down x what? 1, 3, 3, 1 is like you have 1 plus x cubed is equal to or x plus 1 cubed. So you can have something like x plus 1 cubed, let's say, is equal to 1 times x cubed plus 3 times x squared plus 3 times x plus 1, right? And then somehow we can use up all these entries, 1, 3, 3, 1, in the same row into a formula, right? Now, certain number also have this property. Amazing. Okay, so let's take a look of this fourth entry. Okay. Okay, third entry first. Okay. So we are going to read it backward. Okay. So this is 1, 1. This is 1, 3, 1. This is 1, 6, 7, 1. Is that okay? Okay. Okay. So how is 1, 3, 1 occurring in a formula? Let's take a look of x squared. X squared. X squared is equal to, I'm claiming, let's verify it together. I'm claiming that it is going to be equal to 1 times x minus 1 plus 3 times x plus 1. Okay, nothing special. I just try to write it as x times x minus 1. Let's verify it. Let me see. 1, 3, 3. Let me see. Did I make a mistake? Let me see. 1, 1, x minus 1. So x squared. No. This is not correct, right? 1761. Oh, so I make a mistake. So this is not like 17. So this, let me see. I made a mistake here. So let me. This is falling. Is it 3? Yeah. 1. Sorry. It should be like this. Okay. It should be like this. Let me try again. So let's try again. So let's try x cubed. Okay. So I'm claiming that this is equal to this one plus 3 x times x minus 1 plus 1 x. Okay. Yeah, this should be. Okay, so this time it is 1, 3, 1. Well, let's double check. Yeah, so I made a mistake here. Let's double check, okay, to see if it is correct. So what is x times x minus 1 times x minus 2? Okay, let's try x times x minus 1 times x minus 2. So it is like x cubed minus 3x squared plus 2x. Is that okay? Right? Good. How about this one? It's going to be 3x squared minus 3x. Is that okay? And then what is it? This is just x, 1x. So if we double check, then we have x cubed there, and then minus 3x squared, and then 3x squared cancels, and then plus 2x minus 3x plus x, it also cancels. Is that okay? Okay. And then we can do, and then what is the next one? Okay, so I'm claiming that what? So how about x to the power 4? Okay, so I can have x to the power 4. So for x to the power 4, I look at the 1, 2, 3, 4, the fourth row, the row that is related to this 4, then I'm claiming that this is going to be 1 times x, x minus 1, x minus 2, x minus 3, plus 6 times x, x minus 1, x minus 2, plus 7 x, x minus 1, and then finally plus 1x. Is that okay? Well, let's see. This time more tedious, but these are the terms. So we are reading this backward. We have 1 here, we have 6 here, we have 7 here, and then we have 1 here. Is that okay? Let's double check to see if it is correct. So anyone can explain this? Yeah. Let's be lazy. Just check for the x4 term, x3 term, x term, and then x squared term. We missed the x cubed term. Is that okay? No. Let's x4, x3, x2, x1. We can actually check everyone. Okay. So if you look at this, this is the only term that has 4x. All the terms here, this has only 3x, 2x, and 1x. Am I correct? Right? So this is the only term that you can have x to the power 4. And then you see that there is just one of them, x to the power 4. X times x times x times x. So we get x to the power 4. Is that okay? Okay. Now, how about x cubed? How many x cubed terms are there? So these two things will get x cubed terms. These are the two things that will get x cubed terms. To get x cubed, we must be choosing 3x here and a constant here. Is that okay? So we have minus 1x cubed, and then minus 2x cubed, and then minus 3x cubed. So altogether, there are minus 6x cubed. Is that okay? Does that make sense? Okay. And this one will balance it. We have 6x, so we have 6 times x cubed. So the number of x cubed term will be minus 6 plus 6. So there are 0 x cubed term. Is that okay? How about x squared term? Yeah, don't be lazy. X squared term, how many are there? So x squared term here, you need to pick any 2x here, and then you have these two, you have these two, you have these two, and whatever. Am I correct? So how can we get the x squared? So it must be 1 and 2 together, we get 2. 2 and 3 together, we get 6. So altogether 8 so far. And then 1 and 3 together, we get 11. Is that okay? 11. Okay. Did I miss anything? So let's do it again. 1 and 2, we get 2. 2 and 3, we get 6. So altogether 8 so far. And then 1 and 3, you get 11. So that's 11. 11. So let's write down 11. X squared times 11. Okay. And it is plus 11. Yeah, it is plus 11. Okay. This one, you want to get x squared. And then this one, you have minus 1 times 6. And then minus 2 times 6. Is that okay? So altogether, it is minus 18. Is that okay? Does that make sense? Minus 18. Minus this time. And then this one, 7x. So plus 7. So 11 minus 18 plus 7? 0. So you have 0 x squared term overall. And then how about the number of x? The number of x is easy. So is it easy? Yeah, the number of x is just like you must multiply x here. So you look at the constant term of these three things. Minus 1 times minus 2 times minus 3. You get minus 6. And then this one is plus 12. Is that okay? And then you get minus 7. And then you get plus 1. Is that okay? So again, amazingly, it is 0. Okay? So this thing, amazing. Every row is correct. So you can actually write it compactly here as 1 times x to the power 4. But then this is a falling power. You start from x and then x minus 1, and then plus 6 times x to the power 3, again falling power, plus 7x to the power 2 falling power, and then plus 1x to the power falling. And then for this one, this is equal to 1 times x to the power 3 falling plus 3 times x to the power 2 falling plus 1 times x to the power falling. So this is a very nice representation. Okay, now, why is it correct? Why? Why is it correct? Let's focus on the case x to the power 4. Let's focus on the case. So for x to the power 4, we have this one. X to the power 4 is equal to 1 times x to the power 4 falling plus 6 times x to the power 3 falling. Is that okay? Plus 7 times x to the power 2 falling plus 1 times x to the power 1 x to the power 1 falling. Okay. All of these are Stirling numbers, recall. So what is it? So this is S what? R is equal to 4, and then N is equal to 4. Am I correct? And this one, this is S, R is equal to 4. Am I correct? And then N is equal to 3. Eh, no. Let me see. R, N, right? Yes. And this one, S, 4, 2. And then this one, S, 4, 1. Okay? This 4. This 4 is from the 4th row. So this is actually equal to R. Okay? So today we talk about putting, so we are doing counting problems, everything related to counting problems today, right? So we have R here, right? We don't have N. So let's make it N. Let's don't look at X as X. Let's think of X as N. Okay, so N is the number of boxes. So if I change X to 5, okay, perhaps I copy it here. Let's say when I change X to 5, does it make sense to have an equation like this? 5 to the power 4, so we want to ask, does it make sense to have 5 to the power 4 is equal to 1 times, so what is it? 1 times, this is 5 to the power 4 falling. 5 to the power 4 falling plus 6 times 5 to the power 3 falling plus 7 times 5 to the power 2 falling plus 1 times 5 to the power 1 falling. Okay, does it make sense to have this thing? So let's try to prove this. Just try, not prove for general X. Let's try to prove this. Just try to prove this. So we try to prove this with the combinatorial argument. Okay. So 5 to the power 4 should be counting something. This one should be counting some other things. This one should be counting some other things, and so on and so forth. Okay. So naturally, what is 5 to the power 4 counting for today? 5 to the power 4. R objects, right? So we have 4 objects. Each object has 5 choices. Number of functions that has 5 elements on this side. So this is counting on this side. We can have 1, 2, 3, 4, 5. And then on this side, we have 4 objects, A, B, C, D. So this is A, B, C, D. How many functions are there from this side to this side? Is that okay? So this will be going to be 5 to the power 4. Does that make sense? Okay. Now this is the total number of functions. And then here, so we want to make some sense about 5 to the power 4 falling. So what is 5 to the power 4 falling? So I have to choose 5, and then I have to choose 4. I have to choose 3, and then I have to choose 2. So which group of functions has this number of ways to choose that? So that means what? That means that for the first item, I have 5 choice. For the second item, I have 4 choice. For the third item, I have 3 choice, and then 2 choice. What's that? They need to be all distinct, right? Right? Okay, so it means that they need to be all distinct. Okay, distinct. So, or you can think of this as injections. Okay, injections. How about this? How about this? 5 to, so we have 6. 6 comes from 4, 3, so we have 3 boxes, right? Okay, maybe not distinct. So how many ways, how many functions such that the total values of A, B, C, D is mapped to 4 values? Does that okay? So 4 values. A, B, C, D consists of 4 values. Is that okay? And how about this one? This is the number of ways that, just this part, is the number of ways that to have A, B, C, D choosing only 3 values to use. Okay, so there are 5 times 4 times 3 ways to select 3 different values for A, B, C, D to use. And then this 6 comes from the different ways that A, B, C, D are mapped to the values. Is that okay? So altogether, this one is the number of functions from this one to this one that uses exactly 3 values. Is that okay? And then this is the number of functions that uses exactly 2 values. Is that okay? And this is the number of functions that it uses exactly 1 value. Is that okay? So we are breaking down the counting problem. Breaking down this as a counting problem of how many ways that a function uses exactly 4 values, how many ways that a function uses exactly 3 values, and so on and so forth. Is that okay? Is that okay? So this works. This works for 5, the case where x is equal to 5. Is that okay? This works for x is equal to 5. If you are okay with this so far, could you please raise your hand? Now, amazingly, this does not just work for x is equal to 5. Let's change it to 6. Let's change it to 6. Let's change it to 6. It also works. It also works. Is that okay? This is counting just with 6 items here. It also works for 7. It also works for 8. It also works for 9. Okay. So what does that mean? What does that mean? It means that if you consider this function, let's call it function x. Let's consider that a function x, which is defined as the left-hand side minus the right-hand side. The left-hand side is x to the power 4 minus the right-hand side. X to the power 4 falling plus 6x to the power 3 falling plus 7x to the power 2 falling plus 1 to the power x to the power falling. Let's consider this function. This function is interesting. If you put x is equal to 5, then this number is equal to this number. So it will be 0. Is that okay? If we put 6 here, then it is also 0. If you put 7 here, 0. 8 here, 0. This is a function, right? This is a polynomial of power 4. But it has already, we have already shown that it can have 10 roots. You can put 5 inside, it's a root. 6 here is a root. 7 here is a root. Then what does that mean? Can a function of power 4 has 5 roots? Can it happen? No, it cannot happen, right? So the only way that for this to happen is that this is not a function. This is not a polynomial. This is the constant 0. This is the only case, right? If you find that a certain polynomial form, it has many, many roots, then there's only one thing. It has more roots than its power, then this is only one thing. It has to be equal to 0. So in that sense, once we know how to count the number of surjections or number of functions, then we can use that to prove there are there are infinite many cases for this to hold. And that this implies that this has to be an identity, an equality, no matter what x that you are choosing. Okay, so we have shown that 5 works, 6 works, 7 works. When x is equal to 5, it works. 7 works, 8 works. But how about 1.2? Does it work? Well, 1.2, it works. It is because we have shown that this has to be equal to a big 0 here. So in that case, these two things are always the same, no matter what x you are choosing. And then, so this is generally true. So amazing, right? And then just one last remark. So we call this we talk about SRN today. So this is the Stirling number of the second kind. So how about Stirling number of the first kind? So Stirling number of the first kind is relatively easy to define. You just look at the expansion, x, let's say x minus 1, x minus 2, x minus 3, and so on and so forth. Then the coefficients will form the Stirling number of the first kind. So it would be something like 1, and then minus 6, and then what? Okay, I cross it out. So it's like 1 minus 6, or maybe then 11, and then minus 1, something like this. So it is in the expansion of x to the power k falling, what are the coefficients? The coefficients will correspond to the Stirling number of the first kind. And then if we take absolute value of this, so here it has a sign alternating, plus and then minus and then plus and minus. So if you take the signed, so this is called the signed case for the Stirling number of the first kind. So we can take the absolute value to make it unsigned. And then there are a lot of interesting property between the Stirling number of the first kind and Stirling number of the second kind. So they are highly related. Okay, so I hope you like today's class. Okay, and then let's talk again. Let's meet again on Thursday. Okay, thanks.